All right, I'm going to get started. Hi, everybody. My name is Dustin Getz. This talk is about composable user interfaces. So as front-end developers, we like to think about what's going on in the browser when we write our JavaScript user interfaces. But really, the way we write our code is influenced by a much bigger picture that includes the web service and the way you talk to the web service through HTTP, and also fundamentally by the type of database you're backed by. So we're going to explore, in the context of the whole, the impacts of these choices over the last 20 years and how it impacts the way we write our code, what problems it causes, and then a vision of the future where these problems are hopefully solved. So this quote, which I hope you've read because it was on the screen earlier, is from Pete Hunt, who was working at Facebook at the time. He's an engineering manager, and he was working on the Facebook React JavaScript library at this time. And he's talking about why Facebook doesn't use REST. So the problem is when you write a REST interface, you need to make a lot of requests. Sometimes, if you picture Facebook, you start at your profile, and then you clicked on a picture, and then from a picture you clicked to expand the comments, then from the comments you clicked on your friend's name, and then you clicked on one of their events. You're navigating this graph. And each time you go to a different component of the UI, you had to make another request. And each time you made a request, well, that was latency. It made the battery on your phone drain because the radio turned on, and it had to make it took half a second to get to the database, and then it had to go from in their infrastructure, it had to go talk to the actual database. And it's really slow. And in the old apps 20 years ago, that wasn't that big of a problem because apps were really simple. But today's apps are really complicated. So you just have this nested recursive I/O. And we're going to try to talk about how to fix that. But that's what's bad about REST. But first let's talk about what's really good about REST, because it's been around for so long. So this is an HTML form. And I've actually implemented the form in two different ways. At the top, I've used actual HTML, and then the bottom, I've used a JSON data structure, which has the same information. Now, if you ignore the JSON, just look at the HTML at first. When this HTML hits a web browser, the web browser is written in C++, but it knows how to render this form. It knows how to talk to this demo form.asp backend on the server. It knows it needs to generate a post HTTP request. It knows the labels. It knows to draw a text input, not a date input, not an email input, but a text input. It knows when I send the payload to the server, what is the payload shaped like? It knows to use this first name string as the name of the parameter sent to the server. And this is all, you didn't have to code special JavaScript to get this to work, nor do you have to write C++ plugins to inject into your web browser process to make this work. It's fully data-driven. So this is the goal of REST, was to have a data-driven user interface that just worked without having to write code. So today's apps look more like a JSON web service that you code in JavaScript. But fundamentally, you could represent the same information in a JSON data structure. It's literally the same information copied and pasted. You've got the URL right here. You've got the type of HTTP request. You could render this form just by looking at this data structure. You don't have to write any special JavaScript other than some that is fully general to render this form. They're both fully self-describing. But most forms are more complicated than that. So here's a real form from an app I built, and you can see there's combo boxes in it. So this program combo box right here with the arrow, it's got A035 inside of it, but really, in your data structure sent over the wire, that was probably an ID. In the database, that's a foreign key joined to another table. And not only that, this combo box, if I click on the arrow, there's combo box options in that, and that was backed by a database query. So real forms are a lot more complicated. So when you think about how you might code this, if you wanted to build this fully general, it might look something like this. You've got links between it. So this data structure, just squint at it, don't look at it too closely. It's basically got two main sections, a top section and the bottom section. The top section is the data. It's got the attribute and the value. The bottom section is the fully general metadata to describe the form. So this bottom section right here, it has data type string and name, community name. So that would correspond to like the string type in one of these text inputs. You could have a different one that has data type ref, like this one here, and note it has options since it's data type ref. It's a reference to something else. You need a URL to like the query backing that combo box. So this is data type ref. Now, this is very nice. This is fully general. If I want to like browse through this, like I can click on these links in my web browser and I can kind of explore the data underneath my application. Like if I want to draw the combo box options, you can kind of like in your head picture the JavaScript you might write. You'd say, well, I want to traverse this link for the label of this reference, and I want to turn this link for the label of this reference, and I need to traverse this link to load the combo box options. And this is really elegant. You could write a fully general client that let you, like once you wrote the library, you wouldn't have to write any more code. You could just configure your data, have the web service drive the data, and have all these forms just happen for free. But the problem is like what Pete Hunt was talking about. This is generating a lot of requests. This fully abstract data-driven form is really chatty. It talks over network all the time, and thus it's really slow. So this is a real application, not like a fully general application. Like this is concrete practice line of business application. But you can see here's a really complicated form. So the question basically we have as programmers is like how far can we go? Like how metadata driven is this form really? Like there's some small problems with it. Like you can see there's this little pin icon right here. So if I it's like a sticky feature. Like if I sticky this, then there's certain business logic that happens in that. So that's hard to make fully general. But how about this table? Like a table is kind of like a form inside a form. Like just like this form was backed by a query, well each row, the rows in this table were also backed by a query. So if you could make it fully general, like you could kind of picture not having to write any code to make this form. You just configure the data and then use a library, provided like some open source library. But of course that's not how we write apps in real life. And the problem is, to make this fully general, you'd have to make so many requests, like each one of those requests can fail. Each one of those requests is asynchronous. You have to wire a callback, and what if it fails? Well, you need to use like a promise abstraction or something to make sure the errors backpropagate properly so they get handled. So in practice, we don't really use REST that much to write our applications because it's just too slow. You know, in real life, the query backing this form, it executed in one request. I wrote special code in Java in the back end that like joined together all the pieces of data in one database query, and then I wrote like JavaScript on the front end that loaded the whole thing in one query, because that's how you make it fast. But it could be better. So here's a real life application that actually is fully data driven, and we're going to talk about this a lot. So again, since it is fully data driven, like with the links that you can follow fully generally, like you could like click this edit button to expand like this attribute. Like I want to see the form inside a form just by following this reference. So for example, here it is running live. So if I click edit, it'll come back. There we go. So if I click the edit button, you can see the inner blue line, there's a form inside a form here. So if we coded our application in REST where everything was fully general with link following, you've got something like the World Wide Web where you can just click around links and do what you got to do and then hit the browser back button to go back to where you were. And things are really good. So again, to drive home the point about making a lot of requests, if we were going all in on this model of making everything link traversable, like this is what a collection endpoint looks like. There's a result set from SQL that basically gave you a list of IDs, and each one of those IDs needs to be further resolved to get the record. So to actually draw this in a browser, you'd have to make like, well, there's 20 records here, so that's 20 requests. Each one of these records might have further links to other records, so it's 20 times n requests. So it's obviously just not something that we can do today. So this is why we don't write applications like this today. It just doesn't work. So instead, we end up with what's called the backend for front-end pattern. So what this is, like really, we've got a database state, and it would be nice if we could just like write our business logic once, run it right in front of the database, and have all of our different types of clients talk to this one service, and the one service could serve all of them. So if I have like my Facebook web property running in a browser, it's just going to follow some links to get the information it needs. Now that information is different than what the iOS app needs, and it's different than what the Android app needs, and definitely the tablet app. Like it's going to follow a different set of links and a different set of information. But since that's not fast enough, we end up needing to split out a bunch of backends also. So each one of these is duplicating the business logic special for each one. Like programmers have to write code, and you need database admins to like write custom database queries. This is why programming is hard. Like this is why it costs like so much money and years of engineering time to make all these apps. So this is a really big problem today. So that leads us to our problem statement. When we write code on the front end and on the back end, there's a large surface area of asynchronous code because at any point, like maybe the user is going to click on something else and need to load more data. Now, anywhere where the front end is making a network request, well, that's also performance critical. Like a network request could take a lot of time. Like the line of business application I had on the screen, like that application is used in Asia and the servers are in America. And those poor people like working the workflow system in that, like there's 6 seconds of lag for each request in the application, like it's doing, you know, at least 10 of them. Like we try our best to manage that by writing all this special code, and everybody, like it's just really bad. You know, the users hate it and the developers hate it, and there's bugs and errors and everything's really hard. And also there's a large, like any of these requests can fail. So when we write our code, our entire front-end application kind of has this like singleton threaded through it, which is asynchronous and it's slow and it's failure prone. And every line of code in your application, like when you need to consider that like it can fail, it can be asynchronous. Like it's just really messy. Like it's hard to test. And the biggest problem is like it has to be hand optimized. You can't write a fully general client, which is why we have to write, like that's why we need programmers today, to write all this hand optimized code. So I'm going to try to make this more concrete by looking at code. So Kendo UI is like a library for widgets, and I'm going to pick on them because they're one of the best ones. So when you configure a Kendo combo box, like you say, okay, I want a combo box, and the programmer needs to come in here and say, okay, well, I need a data source for my combo box options. Okay, this looks pretty easy. Like I put the options right here. This is great. I attach it to the DOM. Like this isn't so bad. Like here's what it looks like. But the problem is, like what happens when you want to make something real, like where there's a database query underneath? You know, then I need to go look at the documentation, and like there's like 20 methods I need to understand. Like this data method here. Do you think that this does I/O in Kendo if you call this? Like it turns out that it depends. And the only reason I know that is because I had to find out by stepping through the code in the debugger to figure out why the heck a random request that I didn't expect to happen was being generated. So what does this do to our code? So I wrote this code. This is again the code behind this application I'm demonstrating to you. And look at this comment that I've made real big. The value is just an ID. We need to fetch data from the server to get the display value. So that means like if like I have a JSON structure with an ID here in this combo box, like that's not enough to draw it. I need to go load like the label. So you have to write like an if statement, and I had to write 15 lines of code around this. And by looking at this code, could you point at the lines of code that are going to fail? Like we had to load data. We had to talk to the server just to draw this label because we don't know if we have the data or not. And this can fail. And looking at this code right now, I see that I'm using a promise, and there's no error handling callback. Like if this request dies, like this is a bug in a production application that I wrote like a couple years ago. The bug is probably still there. You know, it's just not possible to build correctly. Everything is too complicated. So I think that's a bait and switch. Like what we want is like a nice simple way to build our UI components by just like composing data and describing data. Like what's so hard about a form? You know, and it turns out that we have to do all these like sequencing statements and reason about all these failure prone things in order just to make an application today. So that sort of brings us back to the beginning. What does Pete Hunt mean when he says Facebook doesn't use REST? Well, every time you do data fetching, it can fail, it's asynchronous, it's just poisonous. Like this is why something that's so simple, you can think about it like in your head. Like it takes 10,000 lines of code to do it. Like it shouldn't take 10,000 lines of code to build like that complicated form I showed you. Like it's just a query result set with a form on the side and then a grid inside the form. It shouldn't take a programmer to build this. Like the CEO should be able to build that just by like describing what the data looks like. You shouldn't need a programmer to worry about if it's going to fail or not, or if it's going to be asynchronous, or to figure out the promises. So here's a screenshot from the Chrome profiler. I'm borrowing this from David Nolan's blog, and there's a link. He's the creator of the ClojureScript programming language. He's a really smart guy, great blog. So this profiler, like the reason we use profilers is we want to look at the code as it runs as a whole, and we want to like understand like where the hotspots are. And to understand where the hotspots are, you need to understand the thing as a whole. So looking at this flame chart, where's the hotspot? Like this is what callback code does to a profiler. Each little spike is like a callback, and then it only did a little bitty thing, and then it called another callback, and that did a little bitty thing, and then it called another callback. Like it is impossible to optimize. And if you look at a Backbone.js code like running in a browser, like you'll see the screen flickering, and you'll see like the layout freeze, and you'll have like random bugs where they forgot to attach the error handler. Like it's just poisonous to write code this way. This is what it looks like if you use the Facebook React library. The Facebook React library, like one of the ideas behind it is we're going to make writing our front-end code look like writing HTML again. So if you're on the back end, like you're on ASP.NET or JSP or something 15 years ago, you just write like HTML templates and you punch in your data. And you don't worry about the data fetching. The data fetching is done separately. Like you fetch the data and then you render the template. So that's how React does it, and you can see like you can reason about this code now. Like you can keep the whole thing in your head. Like it's an equally complicated application. This is just the flame chart for 2D MVC, but you can see how it fits together. So that's why it's so important that we think about these things. Like when our applications of tomorrow, like in 2020, like we're building bigger and bigger applications, like we need to be able to reason about it like this. Otherwise, we're going to drown in the complexity. We are drowning in the complexity today. And then the complexity is just, why we have to write all this custom code in all these different layers. Like we should really only have to write the business logic once. So, how can we fix this problem? Well, we've been talking about I/O. And what would happen if we could just not do I/O, if we had all the data locally inside of our browser and like served out of cache, like everything's cached in the browser, well now I can just like traverse the edges of the graph without worrying about the cost. And as developers, we're already familiar with a system that is kind of like this. That system is Git. When you think about Git, like it's essentially an immutable time series database. And if you want to ask a question to Git or run a query against Git, well, the first thing you do is you git clone it to your machine. And then you can ask a query like, show me the history of this file. Who is the last person to change this file? That's like a query. And then my coworker can also git clone the database to his machine, and he can run the same query, and you guys are going to get the same answer. And neither of you are going to have to go make a request to github.com to do it, because it's answered out of cache. So I propose that if only we could git clone our entire database into the browser and ignore the security and performance implications of that, a lot of the problems in our code will go away. Like all this failure-prone asynchronous I/O is just going to drop out. So let's talk about how we can model our data as an immutable time series that can be sent to the browser. So this is a really simple database. It's got 3 records in the database. Each record has an ID. Dustin, the name Dustin, has a reference, so like a reference to the country 101. So that you could think of in the database as like a foreign key lookup to this thing which has ID 101, and there's the label USA. So we could take this graph data structure and we could represent it differently. We can represent it as a list of things. So first you say, well, ID 100 has name Dustin, and ID 100 has country, a link to the other country. And if I wanted to change this, if I wanted to say, well, the entity with ID 100 has named Dustin1, I could just append to this list. And like Git, like the last one will win. Like if you have a Git commit to a file and then you make another commit on the same line, the last one wins. So this sort of sets up the ground for allowing us to shape the data in a proper way and send it all to the browser such that we can write a fully general form builder that can like traverse these links conceptually, like it can traverse the link between Dustin and the country, and maybe that has references to something else, like the Facebook example, this really complicated graph, the friend graph, the social graph. We can render this in the browser, and we can do it without generating tons of requests if only the data was locally in cache. And that would solve a lot of problems. There wouldn't be anything asynchronous anymore. There's nothing performance critical. When you type a query, ask Git a question on your machine, like it's not doing I/O, it's operating off of local data, so it's just CPU processing time. You know, we all have gigahertz processors in our pocket right now, like CPU is free. And it also can't fail anymore. Like if you type a command into Git, when's the last time Git had an error that said, hey, I'm sorry, I couldn't go over network to answer your question? Like that's never happened. It can't fail. We've eliminated the possibility of it failing by operating on a local data. So this slide is borrowed from Nikita Prokhorov with permission on his blog, The Web After Tomorrow, which is fascinating. You should read it. And it proposes an immutable time series architecture that addresses the performance and security concerns. So if, like Git, we model our database as an immutable time series. Like you could picture each one of these are just commits against our graph. Well, you can filter it. Like you can now write a filter that says, well, this second step is the code that passed security. Like I'm only allowed to see maybe commits that have my name on it, so I can filter that on the server. Now you can further filter it again. Like maybe your web tier can say, hey, I know what the user's looking at because I know what the URL is on his screen in his browser, so I can predetermine what data he needs to see on his screen. And you can filter it again and send only the data that the person needs to the browser. So how could we implement a system like this? Well, first you need the immutable time series. Second, you also need a way to determine in your web tier how to decide which data to send to the browser, because you can't be sending your entire database down. Even if you filtered your database by what the user is allowed to see and has permissions for, like it could be a gigabyte of data, you can't do that. So we need some like language or platform that lets us run code in both places, the server and the browser. And of course we know JavaScript can do this. If the UI is coded in JavaScript, you can run the UI in Node.js, and by running it, you can determine what the data dependencies are going to be. So you can make sure you send down the data they want. And then it'll never have to make another request ever again, which means your code can be pure functions against local data. It'll never be asynchronous. It'll never fail. You'll never have to write a promise ever again. Never have to manage a callback. So that lets you write code of this. Now, this is ClojureScript code, which is a compiled to JavaScript language. I like to expose people to this language since it's like, you know, it might be the language we're all using in 10 years. It's really powerful. And I'm showing you this because this is a real form that works, and this is the real code that drives it. There's no lies here. Like it's not a staged demo. Like if you pasted this into the ClojureScript compiler, ran it in a browser, you'd get this form. There's no I/O here. There's no promises here. There's nothing asynchronous happening. All we have is a form abstraction that's fully general. Like this CJ form function takes a parameter for the value that you're drawing in the form, and it takes a parameter for the metadata for the form, like the data, like how do I know the types of each thing, and that's it. This thing will never do I/O because it knows that the proper data was sent down to it ahead of time. It knows that it's operating off of local data. So this makes all the complexity, all the problems we have in our front-end code bases, it just makes them all go away. So when people are talking about like, I have this new fancy reactive thing that like makes asynchronous code easier to worry about, like that's really nice, I guess, but like what if it wasn't asynchronous? What if it couldn't fail at all in the first place? What if you never had to coordinate that? Now, since the data is locally, you can actually build ever more powerful forms. So this whole idea of using link navigation to drive our UIs, like you can navigate into this UI by clicking buttons. And again, if the data is inlined, it's not making any requests. So you can make like more powerful UIs than we do today. Because like by removing the complexity, we can just write data-driven code, more flexible code that doesn't have to worry about failure or async. There are some other interesting consequences about it too. So today, if you are typing into a form, like this, what if I'm typing into this little text right here, and this node in the graph also appeared in another place in the graph? Because you can navigate the structure recursively. Like maybe the graph has cycles in it. Like maybe I navigated to my mom's Facebook profile via the comments, and I also navigated to my mom's Facebook profile via the newsfeed. Like I got there, and then I make a change here. Well, it can also update there because we're using the proper data structure. Like if this data is actually backed by a graph, like typing in here is going to make a change to the graph, and you can see it update right here. This is because we're using like the graph data structure on the client instead of just in the server. Because in the past, like if you type it in right here, well, you need to transact that to your database, and then you rerun the queries, and then send that back over the wire, and then you'll see the same value down here. So by removing the I/O, we can also stop denormalizing our UIs. You can also have things like reactive queries. So like if I am typing into a form and it turns out that the thing I just made should show up in the combo box options of this other thing, it can react to that because you didn't have to do any I/O to send the data anywhere. The data is local in the browser process. The queries are running local in the browser process. You can do all this without touching network, which I think is really cool. So in conclusion, it's my opinion that the problems that we see today in our day-to-day code, the reason that these things cost so much money to build and are so buggy and break the web, this can all be solved if we just rethink the way that we're writing our web services. The problem is in the web service and the problem is in the database, but if we stop using a relational database, if we start thinking about things as an immutable time series like Git, it provides the proper primitives in order to start deleting code and complexity from the software we write and use every day. So I'm Dustin Getz. You can follow the research examples. We call it hypercred. And I'll take questions now.
What technologies have you used that you think come close to this? I've seen aspects in a lot of things, but nothing that encompasses everything you talked about.
So the biggest source of complexity, in my opinion, is the database. Because on this slide, like we have to write special custom handcrafted SQL queries like for the Facebook web desktop property versus the iPhone. Like you have to write different database queries that properly join everything. So what we need, I think, is an immutable time series database. And there's only one that I know of, which is an ACID database. It competes in features with SQL, and it's called Datomic.
Yeah, that's what I was thinking of.
Okay, and that's written by the guy who wrote the Clojure programming language. So if you're interested in this, like this is not stuff that like you're going to use in your day job this year, but this is what we hope the web will look like in 5 years. So if you're interested in like forward-looking stuff, like what might the next Ruby on Rails look like, I would check out Rich Hickey's work in the Clojure community.
Is Datomic available on any other frameworks with this Clojure/CodeScript?
Datomic,
Or am I misunderstanding Datomic completely?
Datomic is Java compatible, so Clojure runs on the JVM. You can use, so Datomic is written in Clojure. It can run on any JVM. If you wanted to run it off of the JVM, you would need to like put a web service in front of it, which again starts to introduce these problems. Yes?
Have you seen last-lang.org?
I've not.
It's a language for distributed visual consistent computation with the time series backend. So it's designed to be distributed across hundreds of backends, including people that are offline. And so you could have a piece of form that you would be editing and all that, and when you join it back together, they would all reconverge. It's kind of a cool thing along these lines.
That sounds fascinating. I think that you could build a UI system like this on top of a system like that.
Yes, I think they're complementary.
For sure, yeah. Okay, well, I'll be around here if anyone wants to talk more. Thanks for coming to my talk.
Do you see the security layer and the looking at filter down layer part of the database itself and agnostic of whatever client is talking to it?
So the database, I'm going to go off the mic. The database, there's like a 3-tier system. So you have the database, you have your JVM processes, and then you have the browser. So you can't have the database talking directly to the browser. You need somewhere to run the security. So that would be like the middle thing. But if you think of like the backend for front-end slide right here, you only need one tier. Like the security tier is fully general. You don't have to recode it by hand for each different client. Does that answer your question?
Yeah, that's right. Yeah. Any other questions? I have another one.